An average financial model contains thousands of interconnected cells, presenting a massive density of unstructured data to process. Humans navigate this complexity using visual intuition. We instantly recognize spatial groupings, allowing us to identify a cluster of numbers in the top left corner as a revenue table, without having to read every single cell. We instinctively spot formatting cues. A dense block of text reads as an assumption section, and a standalone box is clearly an embedded chart, all based entirely on how they sit within the visual layout. Fed to an LLM, spatial context is stripped away, reducing the file to a flattened text array. Ambiguity immediately takes over. It cannot differentiate net revenue from gross, nor determine if a number is a raw user input or a computed hidden formula. This structural mismatch places a ceiling on model performance. Because standard frameworks cannot accurately parse the visual context of a financial model, they stall out at roughly 50% accuracy. The industry-standard approach to solving this data problem relies on equipping agents with a library of discrete tools. In practice, this means building 15 or more distinct JSON schemas, each mapping to an individual function, like searching a row or extracting a value. If you allow the agent to call all of these complex tools in parallel at the same time, you quickly hit a massive bottleneck. The agent cannot dynamically combine the results of these concurrent calls in real time to inform its next move. If you force sequential execution instead, the pathway becomes rigid. The agent must wait for one discrete tool to entirely finish processing before it can plan the subsequent step. During complex data exploration, this rigid sequence takes too long. The agent gets bogged down waiting for individual tool returns, leading directly to task timeouts. Witten Labs recognized that by providing an agent with a vast array of sequential JSON tools, developers are essentially just inventing a brittle, inefficient scripting language. Pushing an agent's accuracy past the 50% mark requires abandoning discrete tool schemas in favor of a unified, persistent state Node.js REPL. This diagram maps the standard, rigid multi-agent pipeline. The discovery process runs exactly once at the beginning. If a failure occurs in the execute node, the agent's context is isolated, unable to route back to discovery to pivot its strategy. Attempting to solve this by changing how the data is represented also fails. The most common attempt is converting spreadsheets into standard databases. Translating spreadsheet logic into SQL tables breaks down. SQL requires strict schemas, while source spreadsheets are highly unstructured. Translating the files into XML formats accurately captures the data, but it introduces extreme token bloat, limiting the context window the LLM can actively process. While standalone representations failed, exporting specific subviews in HTML and CSV retained utility for mapping localized spatial layouts. Forcing visual data into rigid schemas or isolating context across multi-agent pipelines completely strips away the environmental awareness the LLM requires to reason effectively. The architectural solution involves collapsing all 15 discrete API tools into a single Node.js REPL interface. This setup separates concerns. JavaScript provides a familiar sandbox for the LLM, while a C backend handles the heavy processing to parse the files. These flowcharts illustrate the interface models. Sequential tools force 15 disconnected calls, creating high latency. Code mode condenses this into one block, but is entirely stateless. The REPL introduces a looped cycle with a persisted memory state between execution runs. Standard code mode is stateless. Unable to save variables, it forces the agent to solve the entire problem in a single shot. To achieve this, the agent generates massive, unwieldy 50-line scripts. If a single line fails, the errors compound and the entire execution crashes. The REPL triggers a distinct behavioral shift. Because variables persist across turns, the agent trusts that its previous work is saved in memory. This memory prompts the agent to write much shorter, targeted scripts for every turn. By executing shorter scripts, the agent interleaves reasoning tokens between discrete actions, allowing it to evaluate its own outputs step by step before moving forward. Persistent memory converts code execution into dynamic self-correction. Breaking work into verifiable steps eliminates the task timeouts that plague sequential tools. Standard coding agents succeed in software development because they rely on established compilers and linters to catch their errors automatically. For an agent to manipulate spreadsheets autonomously, it requires an equivalent, domain-specific verification loop. The first requirement is a custom formula engine capable of calculating spreadsheet logic natively. The second requirement is a custom render engine capable of outputting images of the cell layout, allowing the agent to visually verify formatting. The strict engineering constraint here is that these execution engines must be high fidelity. If the engine doesn't mirror the target environment, the verification loop breaks. This flowchart tracks a hallucination loop. The agent sends valid code for verification. An incomplete formula engine fails to parse it, returning a false error. The agent then degrades its own logic into hallucinated garbage to satisfy the broken engine. An agent's capability for self-correction is strictly bounded by the fidelity of the environment verifying its work. If the engine lies, the agent will fail. Improving an architecture introduces a strict evaluation problem. How do you mathematically guarantee that an agent actually improved from 50% to 92% accuracy? Relying on an LLM as a judge to grade the outputs is insufficient when attempting to validate precise engineering upgrades. With an LLM evaluator, score shifts cannot be reliably attributed. You never know if the score improved because the agent's logic got better or simply because the evaluator's probabilistic whims changed. This schematic details the necessity of deterministic black box testing to solve the attribution problem. A set of test variables is injected directly into the LLM-generated spreadsheet to produce an output matrix. Those exact same variables are simultaneously injected into a golden, human-verified spreadsheet to produce a baseline matrix. The system then compares the two output matrices. By verifying strict mathematical parity, you remove the LLM evaluator from the critical path. When failures do occur in this testing environment, developers must analyze the execution traces to identify non-reasoning errors. Many apparent agent reasoning failures are actually just agent confusion, caused by a bug in the prompts examples or an underlying infrastructure timeout that forces the model into a retry loop. Deterministic testing isolates true model capability from the noise of probabilistic evaluation, allowing you to debug the code instead of guessing at the model's intent. Right now, the REPL is the optimal interface for data manipulation because writing code is currently the strongest modality for state-of-the-art models. These interface paradigms will shift as models eventually achieve native computer use, manipulating environments directly via mouse and keyboard actions. But regardless of how the interface evolves, the requirement for a robust, high-fidelity verification loop remains a permanent architectural rule. The definitive rule for developers right now is clear. If an agent is making sequential tool calls, stop building JSON schemas to solve the problem. Reaching 92% accuracy requires providing the model with a real scripting language backed by persistent state memory.